Hello, everyone. Thank you very much for being with us today. My name is Giacomo Beccari, and on behalf of the ESO Office for Science and within the Directorate for Science, I'm very, very happy to welcome you to the first event of the ESO Cosmic Duologue. So on April 26, 1920, Harlow Shapley and Herbert Curtis gave life to a scientific debate on the scale of the universe, as we all know, which is known as, and remember, as the Great Debate. So certainly that event still represents today a clear example of an inspiring scientific controversy. And I must admit that it is a real great privilege to be today an astronomer and discover and see that after 100 years, many, if not all, of the very important questions that were raised during that great debate were actually answered. But at the same time, I must say that it is a daily experience of, I guess, of any observational or professional astronomers, that, and even probably for every human being, that every time that a question is answered, then new and often unexpected questions show up. So inspired by these considerations, with the Cosmic Duologue series, we would like to present a new platform where via duologues, so basically it is dialogues between two professional astronomers, which internationally recognized experts in their field, we will grasp the current content and the current state of the art of major questions in astronomy and astrophysics. These would also, I would like to show this also as our way as professional astronomers to express our gratitude for the beautiful job that we are allowed, that we can do every day, and especially it is especially important to remind these days where we are all living under very unique and challenging circumstances. Before giving the word to Stefan, which is going to be the chair of our first dialogue today, I would like to thank Federico, Azi, and Stefan himself for accepting our invitation and basically making this event possible today. And I also would like to thank my colleague Henri Boffin for the great and inspiring support and help in organizing the event. Let me also give some technical notes. So the event is meant for professional astronomers, but please consider that this is the first time actually that we use such a platform and such a modality. So please be patient in case there are technical issues. The speakers agreed to record the event, and so the video will be made available on our dedicated ESO Cosmic Duologue web pages. But all attendees that are now many, so we are very happy actually. All attendees, you are all encouraged to make questions using the live chat. I see that already people are posting and saying, oh, hello, this is great. For the ones that do not, please consider that there is a 10 to 15 seconds latency on the stream signal. So the answer can come a bit later than the time that you put it on the chat. For the ones that do not have a Google account, and they can send the questions anytime using either the form that is available on the ESO Cosmic Duologues web pages that we created, or using the email address esoduo2020@eso.org. And we are basically checking the email in real time, so your question will reach us and we will be able to and happy to pass them. So having said that, I would like to thank you all again. I hope you will have an enjoyable event, and I give the word now to Stefan. Thank you very much.
Okay, hello everyone. I hope everybody can. Okay, do we get me? Okay. Good afternoon and good morning, everyone. Thanks a lot for joining. Thanks for giving us the opportunity to talk to you today. Thanks also for allowing me to moderate. Behind me is it's a kind of visual thinking background. We all would like to go back on sky. For the time being, we are not observing on Paranal. So very nice occasion to do those debates and to start with them with the topic dark matter versus, in that sense, modified Newtonian dynamics. I would like to very briefly, before I give the floor to Azi and Federico, introduce the subject. I see Stacy Milgram is also connected, and I took the liberty to take this little cartoon that he also has been showing to illustrate a little bit what is the problem. At the bottom, you see the various observational findings that we have, and which basically nourish then our theories, okay, and let them grow in different directions to try to explain what we observe, and then of course also to create predictions. You see the two basic branches to explain all the faster motions of objects in the universe. It's either some unseen mass, or could it be also a different law of gravity? Okay, so those are then the two main branches with their ramifications. I see also Pavel is connected. Some of you may be interested that there was a debate that in some senses may be a bit similar 10 years ago, held at the University of Bonn between, at the time, Pavel and Simon White. So if you are interested, you could check there. So for those who are a bit maybe unfamiliar with the topic, I just wanted to bring a couple of very basic slides to summarize the history of this. Let's start with dark matter. Dark matter, I would say, was postulated or discovered also almost 100 years ago, only briefly after the Great Debate. That many people look at this paper by Fritz Zwicky from 1933, written at the time in German, about the redshift of extragalactic nebulae. In that paper, most of the context of the text was about the Hubble law, basically, but also there was one subsection here about the dispersion of galaxies in the Coma galaxy cluster. Okay, well, it's still a Coma nebula cluster. But at the time, it was already discovered by Fritz Zwicky that the Doppler velocities of the galaxies in there imply roughly a mass to light ratio of 400. So you need 400 times more dark matter than luminous matter. And it's interesting to see that this is still the order of magnitude of what we think today is the mass to light ratio of Coma. So this is one of the historical milestone papers, I would say, regarding dark matter. And maybe another one you probably all know also is Vera Rubin, who made a lot of very systematic measurements of galaxy rotation curves. And her main finding was this confirmation that many galaxies have this flat rotation curve that you cannot easily explain if the gravity comes, the Newtonian gravity comes from the visible matter only. And this then gives you this typical sketch that many people show. The observed velocity of the rotation is larger than you would expect from only the stars and the mass. And this then introduces the proposal of dark matter to explain that. Okay, so you have more mass, faster rotation. This was the part of dark matter. And as I mentioned before, you can also go sort of the other direction and say, look, let's not talk about different mass, but maybe or more mass, but let's talk about the law of gravity. We know that at very high accelerations, there's already a deviation from the normal Keplerian law. Why not think about sort of the opposite, that it also could deviate at very low accelerations? And this is the paper by Mordechai Milgram from 1983, which has almost 2,000 citations, where he explained or put this up as an alternative to the dark matter scenario. And that theory basically leads, I would say, to some kind of a new natural constant, which is called then A naught, an acceleration constant that would govern the gravitational force at very low accelerations. And one prediction is then, you could maybe focus here on the bottom curve with, I don't remember the name of that Greek symbol, but you probably do. This xi, very smaller than 1, that means that basically the acceleration in the Newtonian regime would be below this A naught, and in that case you get a flat rotation curve. Okay, so that's the very basic, and I would now stop here with my little introduction and give the floor to Asi, who will start with dark matter. And I will also monitor any questions that are coming on the YouTube, okay? And we will then go to them after both Asi and Federico have done their presentations on dark matter and MOND, okay?
Hi, everyone who has joined us today. Thanks for taking the time. And I hope today we can bring you some of the recent research that has been done around dark matter and MOND. I start sharing my screen if you give me a second. You must be able to see my screen now. So I am, for anyone who doesn't know me, I'm a postdoc fellow at the Institute for Computational Cosmology at Durham University. I usually work on simulations of galaxy formation. And here you can see a beautiful picture of Durham on sunny days, reminding ourselves that hopefully the lockdown here will be done soon and we can enjoy the summer weather here. And also I would like to thank the organizers who gave me and Federico the opportunity to discuss some of the Mondian and dark matter research here. So to start with, I should, oh, I'm sorry. So I should just a few disclaimers. One is that I will talk mainly about dark matter, mainly cold dark matter, but I'm not discussing cold versus other flavors of dark matter like warm and self-interacting dark matter. I will mention them here and there when they are relevant, but again, I'm not basically arguing for dark matter against the other ones. And the other one is that I also I want to apologize if to some of my colleagues if your work is not referenced or cited throughout the talk. There is no way I could cite everybody's work, and I'm pretty sure I don't know all of them. So my apologies in advance. So I'm going to talk about mainly the LambdaCold dark matter, or the standard model of cosmology, and why this has been such a success in the past, basically, I would say 2-3 decades. And I would like to emphasize that nowadays that dark matter, which is actually a larger proportion compared to the normal baryonic matter in the universe that we know of, is an important component of this standard model of cosmology. And even though it started to kind of be introduced when people were talking about the rotation curves of galaxies and the dynamical mass of clusters that Stefan was talking about, nowadays it's basically the need for dark matter is more than just this missing mass that we need to explain the internal dynamics of galaxies and clusters. And I'm going to mention just a few of those so we're all on the same page. I should also clarify, just in case for somebody who's not on galaxy formation, what I'm showing here on the left is the energy budget of the universe as we think within this standard model of cosmology that consists of dark energy, which is responsible for the expansion, actually acceleration in the expansion of the universe. This is not what me or Federico are talking about. Then we have the dark matter and ordinary matter, and dark matter is more than ordinary matter. ordinary matter or baryonic matter is what stars and galaxies are made of, and dark matter is the component that basically we are talking about today. And in this standard model, the universe basically starts with a big bang, a hot plasma, and it expands to form the galaxies we know about today. So some of these needs for dark matter, as I mentioned, is now beyond kind of the missing mass that we need for internal dynamics of galaxies and clusters. We all know that cosmic microwave background actually is basically, perhaps I could say, the strongest evidence for the existence of dark matter in order to explain the fluctuations we see in the CMB or cosmic microwave background. We need a component of the matter which is gravitating like dark matter and doesn't interact in any other way with other components. And the other things that where dark matter plays an important role in this paradigm is the large scale distributions of matter in the universe. We explore basically or find, measure these things through various actually things, distribution of galaxies, Lyman alpha forest, baryonic acoustic oscillation, and some others that perhaps when I was making this slide didn't come to my mind. But all of them are pointing to basically this component of the matter that we need, and they fit within the lambda CDM very well. Here you can see the matter power spectrum as predicted by lambda CDM with the red line that you see here, and all these various measurements which are done by various groups and also completely different scales, they follow the power spectrum predicted by lambda CDM extremely well. And this has been one of the great success of this model, that the dark matter is needed in order to explain the distribution of matter and the whole universe as we know of it today. And the next thing that is also quite important is the gravitational lensing. Gravitational lensing, maybe you can say this is still a missing matter, but it's a slightly different missing matter than what we get from the internal, from the internal dynamics of clusters and galaxies, because those are using Newtonian mechanics, and we're talking about motions of galaxies inside a cluster or motions of stars in a galaxy. But through lensing, we have a completely independent measure of what is the mass in a system. This is the bending of light when it passes through a deep gravitational well. And this has also pointed to a missing component of the matter, which is actually quite consistent with what we need for dynamics. I should also emphasize here on the left, I'm showing the predictions from lambda CDM for the mass around galaxies and clusters of different stellar mass observed and actually predicted. The observations are here in small circles sorted by different stellar mass of their hosts. And the lines are coming from lambda CDM simulations with some simple assumptions about which halos host which galaxies. And I would like to emphasize that basically the masses in many of these go beyond where the light is. So the mass is needed outside where we have the baryonic matter. That's another very good success of this framework to explain the mass around objects. And then, of course, we come to the internal dynamics of clusters and galaxies. As some of the important ones are the ones that Stefan mentioned, the dynamics in the clusters or rotation curves of galaxies hint, if we assume Newtonian dynamics, hints towards some missing component of the matter. And I should say it's more than just the rotation curve or actual velocity dispersion in clusters. The other way we can actually see this missing component of the matter is in binary galaxies. For example, in our local group, I was doing a simple calculation the other day. I'm pretty sure others have done it as well. That the Milky Way and M31, in order to be bound, the mass we need is more than just the baryonic mass we observe. And finally, also, galaxy disks with bars are shown to be unstable without some extra mass. I know these can be explained in MOND. I don't want to go to the details. I'm just mentioning different lines of evidence that all come together. I also would like to mention this actually, and it was a fun to read the review from 1979 by Faber and Gallagher about the mass to light ratio in different galaxies, from ellipticals to spirals, and also going through different dynamical arguments why the missing mass is needed. So I would like to then emphasize that the reason that this model has gained quite a bit of attention in the scientific community is that has been very successful in explaining various observations and various scales. In particular, we can actually, it gives predictions that are testable. We start with, for example, fixing the lambda CDM parameters to what CMB predicts. And from there, all the other kind of things that I mentioned, from the larger scale structures, dynamics of galaxies, lensing, and all of them will basically naturally rise within this paradigm. And I think that's the main success of the model. Not only the internal dynamics, it's just we can put basically all pieces of puzzle together, and they all give us the same amount of matter with a property that we know of, or we assume for that. And there are a little bit challenges or discrepancies on the smaller scales, which I will discuss some of them today, actually some of the important ones today, but this is yet to be discussed here. I would like to emphasize that actually big part of the success in this model actually came with the help of numerical simulations. Basically, we cannot find the exact distributions of matter using pen and papers, and we need numerical simulations to solve gravitational equations for us. And we start from a initial condition that the CMB tells us. We basically give it to computers and we let them do the numerical calculations for us, and they can predict the growth of the structures over time. On the right here, actually, you can see me in the supercomputer machine room in Durham University. And these are the machines that are running the simulations for the groups here, and similar type of machines for other groups. And on the bottom, actually, you can see an example of what happens when we start from Big Bang, where the distribution of matter is relatively more homogeneous. There are smaller fluctuations, and as the time goes by and more structures form, basically the structures form from those small fluctuations at the beginning, and the matter distribution we see today in the universe, according to this model, is what you can see on the right. It's quite a complex pattern that we call cosmic web. So actually, these predictions are robust for this model, and actually for also I would say for some flavors, like cold flavors of warm dark matter, some warm dark matter model, and self-interacting dark matters as well. So we get this basically cosmic web structure coming out of lambda CDM that you can see in the poster here in the background, and you can look at the zoom into different regions of that. And these are the predictions that the model gives us, that it basically the cosmic web rises from these initial fluctuations. It's a hierarchical growth of structure paradigm. It's a clumpy, and by that I mean, if you look at this picture has quite a bit of dark matter substructures around the galaxy cluster. So there are small structures, or a lot of small mass structures everywhere. And also it gives us predictions for the halo mass functions and the distribution of dark matter inside halos. I would like to emphasize one of my favorite images of how basically the distributions of galaxies look like when we coming out of the simulations, which is, you can see in the bottom here in the red colors here, are the larger scale distributions of galaxies that comes out of the simulations compared to the observations, some redshift surveys like 2DF and Sloan and CFA And we can see that basically the larger scale distributions are produced very well. And these has been also quantitatively have been compared using, I mentioned before, matter power spectrum, 2-point correlation function, 3-point correlation function, and larger order of mass distribution. Something that is, I'm going to go more towards basically galaxies, because that's where basically MOND and dark matter, or where Federico's talk and my talk are connected, in where galaxies start to live in dark matter halos. So in this paradigm, well, I already said that the galaxies are forming in the center of the, actually, maybe I can show the previous, the galaxies form in the center of this dark matter halo. So in the center, it's a deep gravitational potential well. Gas can cool and form stars. And that's what, in this paradigm, that's where galaxies are located. But exactly how, which halo hosts what sort of galaxy, or how big the galaxy is in a given halo, what can we learn about that? So here we're looking at on the top left, we're looking at the dark matter halo mass function. That is a direct prediction, actually a direct and robust prediction of dark matter halo mass function in lambda CDM. In the warm dark matter case, below 10 to the 7, it starts to flatten and fall off, but down to about 10 to the 7 or 10 to the 8, even warm dark matter looks the same as the cold dark matter. So we have this steep, relatively steep dark matter halo mass function. And when we look at the galaxies are the other kind of bluish and also the purple point here from different surveys. That's the galaxy stellar mass function we get. And you can see it has actually very different shape to dark matter. And we can now go to the question of which one of these galaxies lives in which one of those halos. A technique which has been widely used and has been verified, I'll get to it, is called abundance matching, which works on a simple and basic assumption, which is intuitive. We'll say the biggest halo hosts the brightest galaxy, second biggest halo, second brightest, and so on. Basically, we just assume that most massive halo hosts the more massive the halo is, the brighter the galaxy it hosts. And it gives us a relation between dark matter mass and galaxy mass. I'm showing an example of that here from a master 2013 abundance matching relation. Here you can see the stellar mass versus halo mass on the left, and stellar mass divided by halo mass as a function of halo mass. It has an interesting shape, which comes from the fact that actually dark matter halo mass function and galaxy mass function behave differently. And the larger halo masses, we're looking at the galaxy clusters. At the knee here, we are looking at the typical spiral galaxies like our own Milky Way, and the lowest mass scales is the scale of dwarf galaxies. It's interesting to look at the stellar mass over halo mass. Actually, basically the peak is where things like Milky Way, galaxies like Milky Way live. Clusters are very less efficient to make stars. And when we go to the dwarf galaxy regime, that's also very inefficient to make stars. This relation has been tested quite a lot on the halo in the cluster scale, so at the high mass end. It has been tested using lensing methods. Actually, one of the plots I showed earlier was using this method. But at the lowest mass scales, that's where things are a bit unclear, and I will talk a little bit about that. But I would like to emphasize that here you can see the stellar mass over halo mass is very small. It means these galaxies are very dark matter dominated. That's why we are interested to look at this regime. And I will quickly talk about some of the problems that actually lambda CDM needs to address, or maybe have addressed, we will see, is about the dwarf galaxy scale. These are called the small scale problems, and I will mention some of the relevant ones here. And so here is one of the first thing that came up is actually we noticed that the dark halo mass function is quite steep. It means actually halos of a galaxy like Milky Way is quite clumpy. It looks like the picture on the left. it has many small dark matter clumps that we call subhalos, and we need to explain basically what is the relation, where are these subhalos. On the contrast, we see some small galaxies, we call them dwarf galaxies around Milky Way, but we have relatively much fewer of them than what we expect in the dark matter. So nowadays we know on the order of 30, 40, till the 40, 50 dwarf galaxies around the Milky Way, but we have thousands or millions of these dark matter subhalos. And the question is, where are all these dark matter clumps or subhalos that live around and that are predicted to be there in the lambda CDM universe, but we don't actually observe them as galaxies. And these numerical simulations and also earlier empirical models like semi-analytic models could relatively actually easy respond to this question. The reason that there seems to be a discrepancy or apparent discrepancy is that the smallest dark matter subhalos do not host any stars. And because some effects that we know, there are star formation happens and supernova feedback as a follow-up to the star formation happens. Also there's cosmic reionization that evaporates some of the gas from the smallest halos. So actually the smallest halos stay basically dark. And the current hydrodynamical simulations, these are full cosmological simulations with gas gas is allowed to cool and form stars and go, and supernova happens. So these models can get the right number of dwarf galaxies. I'm here having some examples in some of these simulations. This is left is from Apostle and right is from Elvis and from the Fire group and Latte. They all get the right stellar mass function, and the kind of price or the consequence that is getting the right number of dwarf galaxies. The consequence it has is that the stellar mass function, stellar mass halo mass relation is very steep. Here you can see in the field, both in the two simulations, this relation is very steep, and that we have to have this in order to get the right number of dwarf galaxies. And again, the price we pay is that many of the little ones have to be empty. And actually, I think that's an interesting predictions from this paradigm, that where are these? The number of those little ones is fewer in a cold, in a warm dark matter scenario. But at the colder the dark matter flavor is, the larger the number of those smaller clumps that we expect. Being aware of the time, I don't want to go to the details of too big to fail and core costs, but I quickly mention it because these were some of the biggest challenges that we had to address. And the too big to fail was related to the fact that, well, we get the right number of satellites, but how about their masses? Do we get their masses right? Here, you're looking at basically the mass profile of these subhalos in these simulations, and what we measure for the real dwarf galaxies with these black points. And it seems that some of the bigger ones do not match any of the observed ones. So these discrepancies, that are the mass of a dwarf galaxy is also consistent with what has been predicted. It appeared to be some discrepancies, which actually was the reason from mainly dark matter only simulations. Hydra simulations these days, basically almost all of them, or all of the ones that I'm aware of, all of them basically can resolve the too big to fail problem by basically appreciating that the stellar mass, halo mass at the low mass end is quite complicated, and it's not very simple one-to-one relation. The fact that actually in hydrodynamical simulations, the mass of these subhalos are a little bit lower because of this supernova feedback and reionization can push some of the baryons out. So these causes that these subhalos will become a bit lower mass. And the other thing that has been mentioned that I will also mention later on is some of this baryonic feedback, this supernovae can actually change a dark matter mass in the center, and they can bring it down, and that's related to the core cost problem. Some simulations predict this behavior, and the consequences for the too big to fail has been discussed in some of these references. And finally, the other flavors of dark matter, like warm dark matter and self-interacting dark matter, can also address this challenge, because the dark matter density is lower in the center in these dark matter models. And at the end, I just want to say we can address the too big to fail problem, but on the kind of slightly, maybe I could say, astrophysical side, we still don't know the exact shape of the stellar mass halo mass relation. Going to the core cost problem, the other prediction of lambda CDM is that the dark matter in the center is steep and it's quite cuspy, as you can see here on the left. When we want to observe this, we observe the rotation curve of galaxies. Rotation curves are essentially mass profiles, and some of them do not look what we expect them to. So they do not look cuspy, that we call them chord. They are shallower in the center. So a cuspy dark matter density would look like its rotation curve or mass profile or circular velocity profile will follow the green one here. But some of the observed galaxies, this is from a real observed galaxy, the blue ones, do not follow that. This has been called the core cost problem, has also been called the diversity of rotation curves, meaning some galaxies, like the one on the left, follow the lambda CDM predictions, and some of them that you can see on the right are either shallower or steeper. How we can address this? There are various lines. Which one is the exact solution? It's not clear, but I think it's not directly related to the MOND. So I'll just very quickly bring some of the reasons, and hopefully, if people can go to the slides and look at some of the references, that maybe the rotation curves are not giving us accurate mass estimates. Maybe the baryons that like as I mentioned, supernova feedback can make cores in galaxies. Also, alternative dark matter models like warm dark matter or self-interacting dark matter also change the inner slope of the dark matter density. They can also give us some chord profiles and address this. I would like to slightly move to the MOND and basically segue to Federico in the last maybe a minute above time. Hopefully I can go. Stefan, can I go for like 2-3 minutes?
Yeah, it's okay.
All right.
Thank you.
So the last piece I want to talk about is Federico actually will expand on this quite a lot, so I will just very briefly mention it. That when we look at the rotation curves of galaxies, they seem to follow some trends that is called radial acceleration relation. Here you're looking at the total acceleration, which is probed by the rotation curve, G ops, or observed or total acceleration. And on the bottom axis, this is surface brightness of galaxies in units of acceleration. It's essentially when we stack, these are spark samples from Federico, actually, you stack all these rotation curves, and they seem to be basically a correlation with a small scatter between the observed acceleration and the surface brightness. And it very well follow what MOND is predicting, which is actually the solid black line here. And this has been one of the kind of the main parameter space that is being discussed in MOND. Again, I leave the details to Federico. I just want to basically address what does this mean for lambda CDM, or can we get this relation in lambda CDM or not? So we, one of my colleagues, Aaron Ludlaw, had actually looked at this in the hydrodynamical simulations of Eagle and Apostle. And this is exactly the same kind of space. You're looking at the total acceleration on the y-axis and the surface brightness on the x. And these galaxies from Eagle and Apostle also follow the spark trend, which is here highlighted in a light gray in the background. By the way, some other works and some other simulations also shown that. And the other interesting thing that is actually being predicted from these simulations is that when we go to a lower acceleration here, what comes out of the simulations is that it becomes more or less flat, and it diverges from what MOND is predicting. I will get back to that in a second. I just want to say that basically this relation is naturally produced in lambda CDM, and it's simply the outcome of the stellar mass halo mass function, stellar mass halo mass relation and stellar mass size relation. Basically, galaxies do not populate halos randomly. There is a stellar mass halo mass relation, and galaxies have some sizes that correlate with their stellar mass. And this naturally gives rise to this relation between the total acceleration and the surface brightness. And just as a footnote, there's also a sub-discussion on the self-interacting versions of these. You can look at the cited work here. Something I'd like to basically mention, hopefully either Federico or maybe in the Q&A, we'll get back to that. Some of the galaxies with the biggest cores that are troublesome for lambda CDM also do not follow this raw relation. So here are two examples from this paper by Julio Navarro and myself and one of the co-authors. This is another galaxy actually we saw it before. It has a huge core in the center based on its rotation curve. And here we can see that it actually does not follow the raw relation. This is the shade, the region here is coming from spark. This is from Federico's spark sample. I'm just plotting the median and the scatter. So these galaxies that are again troublesome in lambda CDM, they have cores. They are also hard to understand in the MOND regime as well. And the other galaxies that could be also a problem that needs to be discussed further are dwarf galaxies. I mentioned before that in the low acceleration, we expected, maybe I go back to that slide. In the low acceleration, the lambda CDM predicts actually the relation becomes flat at around -11 or something, while the MOND keeps going down. And when I plot dwarf galaxies of local group on this plane, that's what we get. The MOND prediction is in dotted lines, and the dwarf galaxies are all the points here. And it's true that there's a larger scatter here, but I just want to say that lambda CDM can just naturally explain this scatter by the fact that these dwarf galaxies, many of them have been stripped. Actually, on the right, you can see results from the Apostle simulations that satellites that haven't lost any mass follow these red colors here, go to a mean, and if they lose mass due to tidal stripping, they come down, and actually the ones that have lost a lot of mass become closer to the MOND prediction here. And I think the tidal stripping can be a natural explanation for the scatter we see here. And one last point, it's a bit related. Basically, when I look at the predicted velocity dispersion of dwarf galaxies in MOND versus what we observe, so we're looking at y-axis velocity dispersion predicted in MOND and x-axis observed velocity dispersion. There seems to be a big discrepancy at the ultra-faint regime. Actually, many of these points here are ultra-faint galaxies. By the way, I included some approximation for the external field effects following McGough 2013. And actually, many of these ones are dominated by external field effects. And they are all systematically lower. I know if they're not in equilibrium, we cannot apply that formalism, but again, just to put it out there that at least at face value, they seem to be a big discrepancy between what we observe and what MOND is predicting. And I'll stop here with basically, oops, I don't know why the last one appeared here, with my conclusions here, or food for thought, or some challenges that we need to understand. Within the lambda CDM, it's the existence of cores, and basically the stellar mass halo mass relation, the existence of dark subhalos that if we find any, that's kind of a telltale for dark matter. And the two topics that I didn't get to discuss, hopefully in the Q&A we can touch on them, is the plane of satellites and existence of compact galaxy groups. And in the MOND, again, I'm hoping that the dwarf spheroidal regime, we can discuss it at some point. And the fact that the MOND still needs to basically explain larger scale structure, lensing, and CMB is kind of a big question that needs to be addressed by MOND. And I stop here.
Okay, thanks a lot, Azi. I hope you can, do you see me now? Probably not yet, probably soon. So great, I will now give the floor right away, okay, to Federico for his talk on MOND. And as I said, I'm taking notes of the questions that are coming up in the chat, and we will deal with them after the two presentations. Okay, thanks a lot.
Thank you, Stefan. Good morning, good afternoon, and good evening to everybody, depending on your time zone. First of all, I would like to thank ESO and the organizers of this event for inviting me. I was asked to give a perspective on MOND, but I would actually like to start with a very basic statement about what do we really mean with dark matter. It's common to read books and articles saying that we need dark matter in order to explain the dynamics of galaxies, the dynamics of galaxy clusters, the properties of the cosmic microwave background, and the emergence of the large-scale structure out of the perturbations on the CMB. But what these observations are really telling us at a fundamental level is that standard gravity, GR plus Newton, and the standard model of particle physics don't work together. So the standard approach is to modify it and extend the standard model of particle physics by introducing new hypothetical particles, but it's equally plausible, at least from a conceptual point of view, to go and modify the gravitational law. So this has been tried by several teams and several people, and many modified gravity theories have actually failed. But I think there is one theory that is still promising in this respect, and this is modified Newtonian dynamics or Milgramian dynamics, in honor of Milgram, who proposed this theory in a series of 3 papers in 1983. It's important to keep in mind that MOND is a general paradigm that includes several different non-relativistic theories as well as relativistic extensions. Therefore, when we test MOND, we have to be very clear whether we are testing the general predictions of the general paradigm or whether we are testing some specific predictions of a specific flavor of MOND. In this presentation, I will mostly focus on the general paradigm and the general predictions. At the non-relativistic level, this is based on 3 simple postulates. The first one is that there is a new constant of physics called A0, which has the dimensions of acceleration. And this constant plays a similar role as the speed of light in relativity and the Planck constant in quantum mechanics. Essentially, it sets the boundary between the classical laws of physics and the new physics. For accelerations much larger than A0, we have a correspondence principle in order to recover exactly Newtonian dynamics. So essentially, the kinetic observed acceleration of a particle, which is defined as usual as the second order derivative of space with respect to time, is equal to the Newtonian acceleration, or more precisely to the Newtonian gravitational field that we can calculate by solving the Poisson equation for the given distribution of matter. At accelerations much smaller than A0, we enter in the new physics regime, and here we assume a new symmetry of space-time, which is scale invariance. Essentially, the solutions of a problem should be invariant under a dilatation of both space and time by a constant factor lambda. And it's possible to demonstrate that if we impose scale invariance at low accelerations, the acceleration should be equal to the square root of Gn times A0. Now, in the specific case of a circular orbit at a large radii in a galaxy, the acceleration is simply v squared over r, whereas Gn is given by the Newton law. And so you can see that the radial dependence cancel out, and therefore we obtain flat rotation curves at large radii, since the velocity depends only on the enclosed mass. What I find remarkable about MOND is that these 3 simple postulates lead to a number of general predictions that we can test. And actually, most of these predictions appear in the original abstract from Milgram 1983, and they were clearly stated in a very precise and ordered way. So I am an observational astronomer, therefore my job here is to go through this list of results and prediction and check whether they are consistent with present-day observational data or not. So the first one concerns asymptotically flat rotation curves at large radii. Strictly speaking, this is not a prediction because flat rotation curves were known before 1983, but Milgram has elevated this observational evidence to a law of nature that each and every galaxy should follow. So today the observational evidence look like this. This is a compilation of 175 galaxies that we call SPARC, for which we have Spitzer photometry at 3.6 micron that provides a very good estimate for the stellar mass of a galaxy. And we also have accurate rotation curves from spatially resolved H1 data. So here the rotation curves are color-coded by the total luminosity at 3.6 micron. You can clearly see that at each luminosity, the rotation curves tend to become flat as long as they are traced far out. And there are actually some exceptional cases where the rotation curve remains flat out to hundreds of kiloparsec from the galaxy center. So we can put a green tick mark corresponding to point number 1 and move to point number 2, which concern the Calofficial relation. This is a fundamental prediction of MOND, indeed appears twice in the abstract, but it's important to understand the historical context. In 1983, we knew the classic Calofficial relation, which is an empirical correlation between the luminosity of a galaxy, which is a proxy for the stellar mass, and the width of the H1 line, which is a rough proxy for the rotation velocity. In the 80s, the slope of the Calofficial relation was strongly debated and constrained between roughly 2 and 5. And actually, it was also debated whether every galaxy was following the Calofficial relation or whether this relation applies only to some specific galaxy type. So this simple statement here by Milgram actually contains 4 independent predictions. The first one is that the luminosity in the Calofficial plane should be replaced with the total baryonic mass, which is given by the sum of stars as well as gas. The second is that the H1 line width should be replaced with a very precise definition of velocity. In theory, we would like to know the velocity at infinity. In practice, this is never accessible with observations, but we can measure the mean velocity along the flat part of the rotation curves. Third, the slope must be equal to 4. And finally, there should be no dependence on galaxy size or surface brightness. And this is quite important because if we do a simple Newtonian calculation, we can derive a Calofficial-like relationship, but there is also this dependence on the surface density of the baryons. So let's look at the present-day observational situation. On the left, you see the stellar mass Calofficial relation, which is quite tight at high masses, typical of spiral galaxies. But as we move down in mass, around roughly 10 to the 9 solar masses, galaxies start to deviate from this relation and the scatter increase. This happens because we enter in the regime of gas-dominated dwarf galaxies, where the mass in gas can be much larger than the mass in stars. If we now replace the stellar mass with the total baryonic mass given by the sum of stars and gas, we actually recover a single linear relationship that extends for more than 5 orders of magnitude. In these plots, the solid line show a fit fixing the slope to 4 and using only one free parameter, which is the normalization, that can be used to set the value of H0. So you can see that a slope of 4 is perfectly consistent with the data. Moreover, the galaxies are color-coded by the effective surface brightness. Therefore, you can see that essentially galaxies follow the same Calofficial relation independently of their surface brightness. Now we can also ask the question of which velocity best correlates with the total baryonic mass. So here you see 6 different versions of the baryonic Calofficial relation considering different definitions for the velocity. On the top left, we have V flat. These are 2 different definitions for the H1 line width, and in the bottom, we have velocities at some specific radii in a galaxy, which are typically representative of the stellar component. And remarkably, V flat gives the tightest baryonic-Calofficial relation. This is a well-established observational result, but is quite counterintuitive because baryons are dynamically important near the center of galaxies, but the baryonic mass best correlates with the velocity at large radii where the dark matter should dominate. It's also possible to extend the baryonic-Calofficial relation by another 4 or 5 orders of magnitude in baryonic mass by considering the dwarf galaxies around the Milky Way and M31. Here we have to be very careful because these objects down here are gas poor, so we cannot directly measure V flat from the gas kinematics, but to a first order we can consider the stellar velocity dispersion. And as you can see, some objects lie on top of the MOND prediction, but other objects are deviating. These are the ultra-faint dwarf galaxies that were also discussed by Asi in her talk, and which also appear to deviate from the radial acceleration relation. So naively, we may say that these objects are ruling out MOND, but what is actually happening is that we can calculate in MOND the strength of tidal forces. We can define a tidal radii and then plot the ratio between the stellar half-light radius and the tidal radius versus the deviation from the Calofficial relation, and you see that there is a correlation. So the most natural interpretation here is that these objects are out of equilibrium because they are tidally affected by the Milky Way, and therefore they should lie off from the baryonic-Calofficial relation. In other terms, MOND is able to tell which galaxies should be in dynamical equilibrium and which galaxies should not. So I think we can put 2 green tick marks and move to item number 3, which concern the Oort discrepancy in the solar neighborhood as well as in external galaxies. And this is related to the vertical dynamics perpendicular to the disk of a galaxy. In my opinion, the observational situation here is not very clear, so we'll simply put a question mark and move to the item number 4, which deals again with the shape of rotation curves, but now at small radii. This is very important because there is a common misconception in the literature that MOND was designed to explain the rotation curves of galaxies. This is not entirely true. MOND was designed to explain the flatness of rotation curves at large radii, which is item number 1. But in the MOND basic postulates, there is no a priori information about the inner shapes of rotation curves. And in particular here, Milgram predicts that for smaller values of the surface density, the velocity rises more slowly to the asymptotic value. Again, the historical context is very important. This is the state of the art in 1983 regarding rotation curves. On the left, you see a compilation of optical data from Vera Rubin and collaborators using optical spectroscopy of ionized gas, whereas on the right, you see a compilation of H1 rotation curves from radio data using the H1 line at 21 centimeter. And in particular, I should mention that H1 rotation curves tend to be much more extended than optical ones, and therefore they allow to identify the mass discrepancy in a much more solid way. But the other important point I want to make here is that in 1983, our samples were mostly limited to high surface brightness, high density galaxies, such as the Milky Way and other spiral galaxies, whereas low surface brightness galaxies were poorly understood. In fact, most of them haven't even been discovered yet. They were lacking from our optical catalogs. However, low surface brightness galaxies are a key test for MOND because in these objects, the acceleration is smaller than A0 at all radii. So they are entirely in the MOND regime, and this is where the MOND prediction become very important. So this is the present day observational situation. These are the same rotation curves that I've shown you before, but now they are plotted in a log-log scale, so we can zoom in the central parts, and they are color-coded by the stellar surface density from the Spitzer images at 3.6 micron. You can clearly see a nice rainbow shape where high surface brightness galaxies rise steeply and become flat, whereas low surface brightness galaxies rise slowly to the asymptotic value. And this is exactly as predicted by Milgram 37 years ago. And I cannot stress enough that essentially this entire blue population of galaxies was not known at all in the 80s. So I can put another green tick mark and move to the item number 5, which concerns the value of the acceleration constant, which can be determined in a few independent ways. The present day best estimate is 1.2 times 10 to the minus 8 centimeters per second. And remarkably, this is equal within the error to the speed of light times the Hubble constant divided by 2 pi. This was already noted in the original paper. It may suggest some connection between MOND and cosmology, or it may just be a numerical coincidence, but it's definitely some food of thoughts for the theoreticians in the audience. So I can now move to the last item, which says that rotation curves calculated on the basis of the observed mass distribution and the modified dynamics should agree with observed velocity curves. This is a bit tricky because the exact prediction depends on a number of auxiliary assumptions in the theory. So a few years ago, in collaboration with Stacy McGaugh and Shane Schomburg, we adopted a different approach. For a given galaxy, we can build a completely Newtonian mass model, which means that given the Spitzer image at 3.6 micron and the gas distribution, we can solve the Poisson equation and therefore compute the so-called baryonic acceleration, which is the acceleration we expect from Newtonian dynamics. And then we have the observed acceleration, which is simply v squared over r from the rotation curves. We can measure these two quantities at different radii for many galaxies in a consistent way, and then we can plot them against each other. And what we find is this remarkable, very tight relationship, which was already mentioned by Asi, which we call the radial acceleration relation. Here, the blue color scale represents 2,700 independent points at different radii in different galaxies. The red squares are simply mean values in acceleration beams, and the dashed line represents one standard deviation from the mean. So there is a very tight and well-defined relationship. And what we have is that at high accelerations, g obs is equal to g bar. There is no need for dark matter. But as we move below a characteristic acceleration scale, we see the dark matter effect, which is essentially how much these points deviate from the dashed line, which represents unity. It is important to understand here that this is a second appearance of H0, which is conceptually different from the baryonic-Calofficial relation, where H0 plays the role of normalization. But remarkably, if we do the fit, we find essentially the same value within the errors. And then at low acceleration, the relation is completely consistent with g obs equal to the square root of g bar times a naught, which is what we expect from scale invariance. Here I should also mention that Adzi showed some galaxies that seems to deviate from this relationship. I think this is not correct because plot should always contain error bars. And when we consider the errors, actually all galaxies are consistent with the same relation. This is the mean error bars that we have on each and every point. And you can actually see by eye that is consistent with the dashed line. So in other words, as far as we can tell right now, this relationship is consistent with having no intrinsic scatter beyond the observational errors. And this is exactly as predicted by Milgram. And actually nowadays, given this diagram, we can determine what is the shape of this new function that interpolates between the Newtonian regime and the deep MOND regime. So I would say that the MOND predictions by Milgram in 1983 are doing relatively well on galaxy scales, but this is actually only half of the story because the same year there was a second paper discussing the implications for galaxy systems. Therefore, binary galaxies, small groups, and clusters of galaxies. I don't have time to go through this in detail. I will simply mention that binary galaxies and galaxy interactions are not a key problem. This is, for example, a MOND simulation that can reproduce very well the antenna galaxies. On the right, you see a recent paper by Milgram investigating 56 galaxy group in the local universe, and the MOND prediction seems to do very well in this context. The real problem is represented by galaxy clusters. This is an old problem going back 20 years ago or more. The issue is the following. If we do a Newtonian analysis of galaxy clusters, the ratio between the dynamical mass and the baryonic mass is very high, indicating the need of dark matter. If we do the same in MOND, ideally, we would like to find a ratio of 1, but in practice, we find a ratio of 2 or 3. So we still need some additional mass, even if we apply the MOND formalism. And this is surely one of the main challenges for MOND from an observational point of view. There has been 3 proposed solutions to this problem. One is that there could be some undetected baryons in the cluster, which should be at least as massive as the intracluster medium. For example, Milgram proposed that there may be in the form of very cold and dense molecular clouds. Here it is important to keep in mind that the Big Bang nucleosynthesis implies that about 30% of the baryons in the universe are missing. We don't know where they are. If we put only 4 or 5% of them in the center of clusters, this problem would be solved. A second option is sterile neutrinos. These are hypothetic particles beyond the standard model of particle physics, but they are strongly motivated by experiments regarding neutrino oscillations and the small neutrino masses. And in the context of MOND, the sterile neutrinos should have a mass of the order of 10 electronvolts. So if you are a particle physicist, this may be an interesting energy regime to look at. And the final option is an extended version of MOND, where the acceleration scale is not exactly constant, but actually depends with the depth of the potential well. So in galaxy clusters, one would have an enhanced MOND behavior. So independently of this, we may also think that galaxy clusters are ruling out MOND, but still I think it's important to ask the question, why did MOND get any prediction right? Or whether there is a deeper meaning of the MOND phenomenology. From a theoretical perspective, there could be 2 possible routes in a MOND context. One is modified gravity, and therefore changing the Poisson equation at the non-relativistic level, and the other one is to modify inertia, therefore changing F equal ma. The modified gravity branch has been well developed over the past 30 years. There is a nonlinear theory that was proposed back in the days by Bekenstein and Milgram in 1984. And there is now also a quasi-linear theory proposed by Milgram in 2009. I should stress that these theories are Lagrangian and they satisfy all the common conservation laws at the non-relativistic level. Nowadays, there are also several relativistic extensions. The most famous one is Teves by Bekenstein 2004. But over the past 15 years, there has been really many ideas out there, and there are now several candidates. I should stress that none of these relativistic theories really feel like a final and fundamental MOND theory. At best, these are effective theories that may be useful in some specific context. For example, many of these theories are able to do gravitational lensing in MOND, but at the moment, the big challenge is definitely reproducing the CMB and the large-scale structure of the universe. This, I think, is the main theoretical challenge for MOND. The other branch has been less well developed, and this is because Milgram has demonstrated that any modified inertia theory should be strongly non-local, which means that we have to give up a number of usual concepts such as the gravitational potential. However, in my opinion, this avenue could be quite interesting because we also know that a formula of this type should hold exactly for circular orbits. And this is what we see empirically in the radial acceleration relation. There are a number of heuristic ideas that may be related to modified inertia, such as the Mach's principle for the origin of inertia, as well as ideas related to quantum vacuum that could connect the acceleration scale with the accelerated expansion of the universe and the cosmological constant, since from a numerical point of view, A0 is roughly c² times the square root of lambda. But I should say that this needs really to be developed more. And there are also other ideas which are roughly related to MOND, such as entropic gravity or new dark matter models, which are constructed in order to give MOND behavior on galaxy scales. To conclude, I would say that in my opinion, it's very difficult to compare MOND with lambda CDM because the two paradigms perform best at different scales. So MOND has been very predictive on galaxy scales, whereas lambda CDM has most of its successes on cosmological scales. So one of the crucial questions is how do we weight the different line of evidence? In general, I have the impression that many physicists and cosmologists think that the CMB and the large-scale structure weight more than individual galaxies, but I was trained as a galactic astronomer, and therefore for me, each individual galaxy is its own universe that we can study and understand in detail. So this highlights that is actually quite important when we have this type of debates to realize that we start from very different backgrounds and perspectives. The other issue is that in MOND, on galaxy scales, we can have a priori predictions, whereas in lambda CDM, we generally have a posteriori reactions. It has been shown by ASI that essentially present-day lambda CDM simulations of galaxy formation can explain nearly everything, but this comes after the fact, after we have discovered a scaling relation or some galaxy property. So this may be viewed as a success for lambda CDM, but in my opinion, it also raises the questions as whether is lambda CDM falsifiable and what would Karl Popper think about this. In this respect, I would like to suggest you two beautiful readings by David Merritt, a nice paper written in 2017, and a recent book which is now available. And finally, I would like to ask the question to everybody, what would make us change our mind about the existence of dark matter? Is there some specific experiments or specific astronomical observation that would force us to give up about searching for a dark matter particle? And I would like to conclude with a more philosophical note, which is a quote from Imre Lakatos, who was a former student of Popper and one of the most prominent philosophers of the past century. And this says that the only relevant evidence is the evidence anticipated by a theory. Thank you.
Thanks, sorry. Thanks a lot, Federico. As I mentioned, I'm monitoring a bit the questions, and also basically based on Federico, what you have brought up. I think I would like to give the word to Azi. Okay. I see maybe one main question that we could bring up is about the prediction power of lambda CDM. There were a few questions in the virtual audience about that, and also Federico brought this up. So Azi, how do you see that? Is it true that lambda CDM is almost entirely, provokingly saying, a reactive theory? Or are there also predictions regarding, for example, small scales that lambda CDM did successfully?
So I think, first of all, Federico, I very much agreed, especially with the point that it's not trivial to compare lambda CDM with MOND, as you just said. They are kind of coming from a slightly different angle. Lambda CDM is kind of performing very well on larger scale, and MOND on the small scale or galaxy scale, if you want to call it. I absolutely agree with that. I'm not sure. Actually, I think I slightly disagree, respectfully, with the point that lambda CDM is not falsifiable. And for example, one thing I can, I'm trying to wrap up my head about on the smallest, I think on the smaller scale, it's quite actually not easy because of the role of the baryons that I think I slightly mentioned, that when we're talking about the galaxy scale, and especially Milky Way galaxy and below, the role of baryons are too much, and there's so much uncertainty. I personally don't think we can kind of maybe we can falsify, let's say, CDM versus SIDM or something, but I have a hard time imagining, at least in the very near future, we can falsify a lambda CDM using the smaller scales. On the other hand, I think on the larger scales, it has many tests that are falsifiable. And well, the thing is, I guess things have been more or less what lambdas. This is the success of the model. Many of the tests it had, or many of the predictions that it had, was following the observations, including larger scale structures, I don't know, lensing and this kind of stuff. So I think all those are, in my personal view, all those are falsifiable predictions of what a mass of a galaxy should be, or what the distributions of matter around a cluster should look like. And these are falsifiable tests, and these are being tested, and they are relatively successful. I'm not by no means, I know very little about larger scale structures, but looking at the general census in the community, that many of the tests that lambda CDM have put forward are consistent with what has been observed. Did I respond to your question, Stefan? If there are any tests, I think the short question is on the smaller scale, it's going to be very hard because of the role of baryons, and especially because of the fact that nowadays Hydra simulations are nowhere near perfect.
Thanks, Asi. Look, I think for the small scales, I think it's understood that you have the baryon coupling sort of problem that makes it difficult for the theory to sort of make predictions, and the theory then is adjusted basically, and using and the coupling is basically improved, what we know, or what we think we know about the coupling. Maybe turning it around, what do you think about the actual proof of dark matter existence? Say, what is your view on experimental research going on?
May I comment on this too?
Please.
Yeah, because I also agree that on small scales, lambda CDM is not very predictive because baryons can be very important. But this raises an important philosophical question or conceptual question, which is, why should baryon physics gives a MOND-like behavior of galaxies? Or in other terms, why has MOND been predictive on galaxy scales? Because right now, what many people are doing is to change the feedback implementation and the baryonic physics implementation in order to give rise essentially to a MOND-like type of law. So it's not clear to me why this should happen. And the other point regards the large scales, which is, in my opinion, not completely true that lambda CDM is entirely predictive. Because even when we look at large scale structure and things like the 2-point correlation function, there is a bias factor, which is an additional free parameter in the theory that regards the role of the baryons. How baryons populate dark matter halos. So it's not complete prediction which comes free of any additional parameter. In my view, one of the real predictions of lambda CDM that comes from the CMB is the value of H0 at the present time. Essentially, you set all the parameters at the CMB scale, you predict it should be 67.4, and now we have many observations that indicates H0 is at least 5 or 6 sigma deviant from this. So this is to say that I don't fully agree with the statement that lambda CDM is predictive on large scales. It has been successful, but successful and predictive is not the same thing.
Well, then that's I guess we're reaching a philosophical difference, because I think some of the things are predictions without extra assumption. One thing I should clarify that I was hoping to, I guess I went over it very quickly, is I don't think we need to basically almost tune much to, even tune at all to get the things like the raw relation right. And by that I mean, I think I even tried in one of the papers, we can even take a toy model that follows the stellar mass, halo mass. By the way, the stellar mass, halo mass doesn't have to come from Hydra simulations. That comes with all uncertainties. As I mentioned, the simple, it's empirical, it's not prediction, but one can assume abundance matching, at least in this context. It's free of at least the uncertainties that comes on the Hydro side, that you have knobs to tune, at least an abundance matching at least down to the scale of 10 to the 7 or 10 to the 8 solar mass for basically bright dwarf galaxies is relatively reliable. And if you just pick again a toy model from that relation, that's basically, again, simple toy model, just follows the raw. So actually, I think it's basically that plane, given that basically both lambda CDM and I guess MOND gives more or less similar predictions in that parameter space. I think perhaps that means it doesn't give us very much. It's not a powerful plane to argue maybe for these between the two models. And I think, Stefan, you specifically asked me about if I can think of any, how to rule out. I think, is that what your question was?
I was no, a direct. I mean, what do you think about experiments, for example, I don't know, at CERN or wherever, to make direct detections of dark matter?
So I think about dark matter, I think there's two aspects. There's this amount of dark matter that we'll talk about in the universe, and if tomorrow a particle in CERN or somewhere I guess people can detect it. I think I think it's a big jump from detecting a particle to actually even claim that's the dark matter we talk about in galaxies and the universe. I think if you're talking about an annihilation signal from cluster centers, that's another story. So for example, one prediction is that, well, depending on the type of the exact flavor of dark matter, some annihilation signal is supposed to come from the center of in the center of, let's say, clusters or other dense structures. That's a prediction. The other one, this is more on CDM versus something else, is this dark subhalos. For example, if we somehow, it could be, I know with the Gaia measurement these days, interaction of people are looking at streams and maybe the potential interactions with subhalos. So if any, I think if any day dark subhalos, we can detect them with a statistical significance. I think that's, at least I personally see it as a very strong prediction that is basically hard to account for in MOND, if one can find these either in clusters or around something like Milky Way. If we don't detect them, makes things complicated because you can always say, oh, dark matter is a bit warm, and those basically subhalos do not exist because it's a warm flavor. That's another kind of debate that I think, yeah, if we do detect them, I think that's a kind of very clear sign. But if we don't detect them, we're back to the same discussion.
Thanks, Asi. Look, there was a bit of a debate between the two of you in the talk with the radial acceleration relation. I will not go back into that too much, because I think the arguments were quite clearly exchanged, and I think the audience can make their own view on that. If I may, I would like to focus on one point more for you, Asi, and then one point for Federico. Both of those points are, in my view, things that seem to be difficult to explain in either theory, and which may be even pointing to the fact that there may not be a correct single theory. Okay, the satellite planes would be for you, Asi, the question, and later to Federico about the problems at cosmological level for MOND. as you mentioned yourself, the overall mass in galaxy clusters, but maybe more specifically, the bullet cluster is always brought up as an example of an empirical proof of dark matter, which would make it very difficult for MOND to survive. So those two questions. First, maybe Asi about the satellite planes. I hope people know what this is about. It's about the orientation of the satellites around the Milky Way and also around other galaxies that is reported to be in contradiction to predictions from Lambda CDM in terms of the probability of getting such constellations. Maybe Asi, you can expand a bit on that.
Yes, sure. So I think as you said, it was perfectly correct. So we see classical satellites of the Milky Way are mainly on a plane that is also seems to be majority of them seems to be co-rotating in this plane. There's also some sort of a plane in M31. It's a slightly different meaning. If you just look at the system, you don't see a plane, but if you try to find, or if you look for the signatures of the plane, a subset of the satellites seem to be on a plane and again seems to be co-rotating. I think, first of all, I should say I'm not an expert in the plane of satellites or the statistical arguments behind it. My take on that is, first of all, the type of planes we're talking about in something like Milky Way and M31, as I mentioned, are quite different. I think for a while the argument was about the Milky Way, and nobody even knew about the M31. So I think one problem is that perhaps if we try to find planes, I guess we'll find them, which is what happens in M31. I'm not saying the plane doesn't exist, but I'm just talking about its statistical significance. Something that I think would kind of convince me to start worrying about this problem is seeing it in more systems. I think just looking at it in Milky Way and M31, I know there are hints of this in, somebody correct me, is that Federico, you know, M101 group?
There is one plane in Centaurus A.
Centaurus A group, yeah, sorry.
Is the third nearest galaxy to us, big nearest galaxy to.
Yeah, but that one, for example, it's a very different system. We see everything in projection, so it has its own complications. I agree, if we keep seeing these planes everywhere, that could be a bit of a problem, but trying to find one, I think it's this look elsewhere effect that that is being discussed in this topic, that we should be careful when we are comparing this. But I agree, if we keep finding this, I start to get a bit worried.
Thanks, Asi. So this look, if people are interested themselves in getting a bit deeper into this, this is the so-called, as you mentioned, look elsewhere effect that is used as a statistical argument a bit in that sense. Federico, if you want to come back on that, but I would like, in principle, that you expand a bit more on the cosmological problems of MOND, maybe about the bullet cluster, and the other problems that you see, if you want to add anything related to what you also said at the very end, to the galaxy clusters in general.
I don't have much to add about the satellite planes. I only want to mention again that essentially the only three major galaxies where we are able with current technology to study this plane all show evidence for it. So it's becoming serious, I think, in my opinion, that the systems where we can do it with the current observational capabilities show evidence for these planes. Regarding the cosmological aspect of MOND, as I said, I think this is the major theoretical challenge. I know that there are several teams working in this perspective along these lines. For example, there is a new Teves-like theory from Scordis and collaborators that seems very promising in this respect. I know this team is working on trying to fit the CMB in this MOND-like context. The results are not out yet, but they look very promising. And now I can maybe mention the bullet cluster. May I share my screen again? Because I happen to have a slide. That's a classic question, so I was prepared. So in case people don't know about the bullet cluster, you see it on the top. Essentially, these are two clusters merging together. And in the standard dark matter paradigm, what happens is that in clusters, we have hot gas, galaxies, and dark matter. So when the two clusters merge together, the gas, which is collisional, should stay roughly in the center, whereas dark matter and galaxies should fly apart because they are collisionless. And this is actually what we see here. Essentially, the green contours is a weak lensing map, which traces the total dynamical mass, essentially. And this is roughly consistent with the distribution of galaxies, whereas the distribution of the hot gas is more concentrated to the center, is off center from the peaks in the weak lensing map. However, this is not really special for MOND, because as I mentioned in my talk, in MOND, we know that there must be at least a factor 2 or 3 of some undetected mass in clusters. And the only additional information that the bullet cluster is giving us is that this additional mass should be collisionless. So for example, here, this is a paper by Angus and collaborators using neutrinos with a mass of 2 eV, and in the bottom you see what you get with a MOND-like theory plus neutrinos, and you can essentially reproduce the convergence map of the bullet cluster very well, because you have this additional form of collisionless dark matter. But it doesn't have to be neutrinos. Any form of matter which is collisionless would do this job. So the bullet cluster is as problematic as any other cluster in the universe for MOND. I would put it in this way. The other interesting thing about the bullet cluster, which is less well known, is that one can estimate the collision speed between the two clusters, and this has to be very high, almost 5,000 kilometers per second, and it's quite rare in lambda CDM to have two clusters that can accelerate at these velocities, whereas this would be quite natural in MOND. So this is an example where a problem for MOND also turns out to be sort of a success, depending on how we weigh the evidence and what we are focusing on.
Thanks, Federico. I mean, maybe a comment from myself. I always find it a bit, unsatisfactory that you need to, or don't you find it unsatisfactory that even in MOND, you then still need to resort to dark matter. Okay, that looks to me, if I may be a bit provoking, in a similar way that maybe then in lambda CDM, you say, at the lower scales, you have the baryon interplay, so you can't really predict things so well. So, and then in MOND, it seems to me that on large scales, there's a comparable problem, for example, with something that has not been detected. How do you see that in comparison? Maybe Azi can make a comment there.
I agree with you, Stefan. This is unsatisfactory, and indeed, I think this is the main observational challenge for MOND-like theories. However, we should also keep in mind that at the time of Zwicky, we did not know about the hot gas in clusters, and this turned out later to be the major baryonic contribution in clusters. So it's maybe perhaps not that crazy to think that there could be some additional undetected baryonic mass in galaxy clusters, since we know from the Big Bang nucleosynthesis that a big fraction of baryons is still missing in the universe. Also, the idea of sterile neutrinos is exotic, but is much better motivated from the point of view of particle physics than WIMPs or axions, since at least for neutrinos, we know clearly that they oscillate, and that we need something beyond the standard model in order to explain the oscillations. So I agree with you, it's not fully satisfactory. It would have been much nicer if clusters were working, but the proposed solutions are not too crazy or too fine-tuned.
Okay, thanks for your view. Azi, do you have something to add?
Not much, but I think just to make things clear, because Federico mentioned axions, WIMP, or sterile neutrinos. At least I was generally talking about all these flavors, for example, sterile neutrinos that are consistent with larger scales. But I think maybe it's a question or comment, I don't know, that if we need those sterile neutrinos on those scales, why we don't have them on the, I don't know, galaxy scale to basically also make up some of the mass in the galaxy scale. But apart from that, I think maybe philosophically, I agree with you, Stefan, that I think that's also, as you said, MOND in the larger scale is becoming in the territory like lambda in the small one, that now we are there's a lot of moving pieces that you kind of lose a little bit of maybe, yeah, it's a bit unsatisfactory.
Let's just keep talking. And here Giacomo, who's the boss, you can tell me when you think we need to close. Federico, I had an impression last year on a,
yes? To say I'm enjoying this too much. Please go ahead, please.
Yeah. Federico, last year we were at the conference in September, and it was about discussing those large-scale problems of MOND, and I had the impression, okay, that by fixing some large-scale, fixing large-scale problem, you maybe come in discrepancy to small-scale. For example, there was a proposal to say, maybe the A0, this constant, is actually not a constant, but it is different in large clusters than it would be at smaller scales. Or the other way around, if you would have to introduce a different A0 on cluster scales to make it fit to the clusters, then it doesn't fit anymore at the galaxy scale. What is your view there?
Okay, I would like to comment first briefly on the neutrino masses, because this is an important point, and is the fact that in a MOND context, the sterile neutrino masses should be indeed of the order of 10 electron volts, because if the mass would be different, they could cluster on galaxy scales and therefore mess up what we get with usual rotation curve fits in MOND. So this is, an auxiliary hypothesis, but also contains a relatively precise prediction for particle physicists, which is the energy window where these sterile neutrinos should be found in order to be consistent with MOND. Okay, so it's an important point. Regarding your other question, yes, of course, it's possible to build theories where A0 varies with the gravitational potential. This is done in a fine-tuned way in order to get galaxies right and galaxy clusters right. So from this point of view, I find this proposed solution less appealing than the dark baryons or the neutrinos, because it doesn't contain an additional prediction. If however, we can develop a full theories where this happen and give us additional predictions that we can test, then it's something that becomes more interesting and we can look at. But I guess my point of view is that every time we add some auxiliary hypothesis to our basic theory, we should make sure that these additional hypotheses make the theory more predictive than before. And this is related, for example, to what Lakatos was proposing in his philosophical view of how the scientific method should work.
Thanks, Federico. Pavel has in the chat, Pavel Krupa has been mentioning, or by email, I don't remember, that dynamical friction is something that would be very strong in dark matter and not so strong in MOND, and that would influence I think the interaction and merger rate of galaxies. So Pavel, I would just ask you if you can put some references or articles about that in the chat so that people have maybe some background on that and then can also form their opinion. I don't want to go there into too much detail on that particular topic. Maybe those who are listening at Chilean institutes, I remember 20 or a bit less than 20 years ago, there was actually Vera Rubin giving a talk at Calan at the Universidad de Chile about the rotation curves and so on. And she was asked, okay, for how long should we continue looking for dark matter particle? Like it was 18 years ago. And she said, well, if in 10 to 20 years we don't find it, we maybe need to rethink. So I just remember that little anecdote.
That's what I tell myself, but maybe in 50 years we haven't found it yet. I don't know.
I mean, clearly, there some. Sorry, yes, Federico.
No, I think this is part of the problem that I tried to brought up at the end, in the sense, for how long should we look for dark matter in labs, right? When, what's a good criterion to stop? Is there such a criterion? Because otherwise, one may wonder whether what we are doing is proper science or not.
That's a good provocative question. I do lack the details how far they have shrunk the parameter space of dark matter particles, right? But my understanding is that there is still a window. Probably the smaller the mass gets, the more you get to a warm dark matter scenario, right?
Yeah, but there's just still orders of magnitude, at least in the mass scale,
Okay.
that is allowed to be probed from WIMP to almost 10 keV or so. So there's a large parameter space, and I completely agree with Federico. I think as a community we should think more about it. There are some things that I think I mentioned that it's kind of the design. I don't know, you find a dark subhalo. I think it will personally convince me. But if you don't find things, how far along do you want to keep searching and searching? And the other thing is, if you find that in a lab, it's still not clear that this is what galaxies are made of. I think we need more astrophysical science.
Well, it's an interesting, maybe philosophical remark that if we prove dark matter particles, then we basically falsify MOND. If we falsify MOND, it does not necessarily mean that we prove dark matter. I mean, we saw that a bit before, that both theories have their problems. Maybe one more thing, okay? This, what was brought up about H0, cosmology H0, and this difference between the like cosmological WMAP value and the value more nearby, right? This is now consolidating as a difference, a highly significant one, between, I mean, you say it's 5, 6 sigma. I think the actual numerical value is less than 10%, right? 5, 6, 7% of the value. What do you think about that? How would that influence lambda CDM, maybe Avi, or MOND? Can the theories be adapted to explain this discrepancy?
So on the lambda CDM side, the discrepancy, well, it exists. I think people are still debating how much of that is actually. I think if it's real discrepancy, I think it can point into interesting scientific results, and if not, actually, it's a slightly more boring that if we find out that it was some sort of a statistical fluke or something. But I think I'm very open. Actually, I'm personally open to all of these, but I'm very open. I think if it's a discrepancy, I think dark energy models are the ones that need to kind of, it's not in the dark matter territory. It's more on the dark energy territory that there are some proposals that if the equation of states for dark energy, for example, changes over time, that could rise to the different H naught. So I think it's not maybe the standard lambda CDM in the sense that I think lambda might need to change with time, or the equation of state need to change with time. But yeah, it's in the area of, I guess, dark energy. And I think actually also modified gravity, but are also looking into this.
Okay, thanks.
But my understanding is that we don't need to kind of change the dark matter by a lot, at least within that framework.
Mm-hmm. Okay. Federico.
So in a MOND context, the discrepancy in the Hubble constant is not too relevant in the sense that there is a numerical coincidence where the acceleration scale is roughly equal to the speed of light times h naught divided by 2 pi, that some theories at the relativistic level may take as an indication to build a full cosmological Mondian theory. However, given the present day errors on A naught, it wouldn't make a difference if it's 67 or 75. But there is this, numerical coincidence that could just be numerology, or it could mean something deeper. I have just a quick comment about what you said on finding a dark matter particle. Here, actually, maybe I'm more positive than Asi, because if we find a dark matter particle in the laboratory, we will also be able, with follow-up experiments, to study its properties. And if they turn out to be the one that we expect for cosmology, then I think, all this debate is done, in my opinion. There would be no good arguments for MOND anymore. But we should still need to explain the MOND phenomenology. So all the scaling relations, like the Calofficial relation, the radial acceleration relation, and so on. So at an empirical level, let's say the Mondian phenomenology will still stay true, but there would be no strong reason anymore to interpret this phenomenology as a modification of gravity or inertia, in my opinion.
Okay. Thanks. I would think this could be actually, from the two of you, nice concluding remarks. I think it was a very lively debate. Probably we may not have gotten to all of the various questions that were submitted, but I hope we could cover the key things that have come up. I hope it was fun. And I hope we can also contribute to making measurements that will everybody allow to discriminate better, and to maybe find something out in 10 or 20 years. Maybe we have another debate then. Giacomo, I would give the word now and the floor to you. Okay. So thanks a lot, Asi and Federico. It was really nice. And thanks for everybody who's listening.
Indeed, first of all, I'm truly fascinated. I would like to congratulate really with Asi and Federico, because you were able to keep 370 people basically on YouTube, and more, and I mean more than 200 people with your exchange. This is really I wish you, I give you all the merits that you have, because you are really great, and I'm really grateful that you made this possible. Really, congratulations, and I wish you all the best for the future career. And I'm very proud that we gave you this chance. I mean, this is really very nice, and I guess I can say from everyone, big applause, because I'm sure, the chat just exploded, I can tell you, on YouTube. I'm also very thank you, Stefan, also for the great chairing of the session. Thank you very much. You've been very great in doing all of this. I would like to say also, it's very interesting to see these new formats working. I see people contributing in the chat. In a sense, is a completely new way with respect to what we do on live, which is probably in certain sense not we cannot replace that, but at least we have a new experience. I can see people contributing. There was exchanges of ideas on the chat. We really think this was great, and it's nice to see this working. We will, just to conclude, I can tell you that we are planning to have more of these. The next one we very likely, but we are not sure 100%, but very likely will be on May 11th. And the topic will be intermediate massive black hole, be or not to be. This is going to be the next duologue. Having said that, again, I would like to thank also everyone for participating, to stay with us. As I said, we will record everything, and just to give you also, it is very likely that we also gonna ask our speakers, Federico and Azi, to summarize in a short summary paper, basically what has been discussed today, so we can leave behind a legacy of this event that I'm pretty sure is going to be remembered in 10 years from now, and even more. So again, thank you very much, everyone. Thank you, Azi. Thank you, Federico. Thank you, Stefan. Thank you, everyone.
Thank you for organizing, and
you.
everybody who listened to us.
Thank you, and see you soon.
Bye.
Goodbye.